This is video 4 in the Sigmastudio series looking at programming the ADAU1701 analog devices digital signal processor using the Shaw Electronics Wondom Kernal processor board as the target hardware. So what we're going to do is look at some filters this afternoon. Or this morning, depending on what time you're watching this video. First thing I'm going to do is, because we're now dealing with perhaps higher quality audio, is to set the sample rate a little higher. So I'm going to set this to 96 kHz, which sets the sampling rate for all of the new blocks that we'll be bringing into the design. Better start a project first of all. New project. 96 kHz, and select our processor, select the E² prom, which never ends up quite in the right place, which is annoying, and the USB interface, and the background of the USB interface is green because the USB interface is connected and working. So, as usual, we're going to go to the schematic window and we're going to find some inputs and outputs. On input, on output. Okay. And I'm going to first of all just initialize a single filter. An nth order filter, single channel, and just put that in to the circuit because I want to compare a couple of filters today. I'm going to look at a stimulus because I want to do a graphical output of what this filter looks like, at least in theory. The proof of the pudding is never seen until the eating, of course. So this is a 6th order filter. I'll just program that into the device. Now if I click on probe, I get a graph comes up. And if I click on stimulus, I get a picture of what that graph looks like. Just change the axes. Make it a bit more useful. So what have we got? The 3 dB point on this particular graph is at 1 kHz, and it's to 60 dB down at 3 kHz. Let's see if we can make that filter a little bit tighter. I'll change it to an 8th order filter. That brings it in a bit closer. Changing from a Butterworth to a Chevy Chev brings it closer still. If we change the type of filter from high pass to low pass, you can see on the graph the theoretical effect that it should have when you implement this filter. So if we wanted to put a single filter in, a high pass to a low pass to make a band pass or whatever we wanted to do, then we can do that. Let's see what else we can do with a filter which we might want to program externally, because it's all very well having this fixed filter in here, but the whole point of things on boards and connected to the real world is we like to adjust things. So let's just go and get another filter. I'm going to go to 2nd order, look up, single channel, and this is an index selectable filter. Okay, this means I can actually program this filter, and I can grow it to have several stages as well. So let's just grow it a little bit. I can grow it and let's add another 3 stages to this filter. So there's essentially 4 filters now in this box, and each one is individually configurable, and the question is, how do we configure them? Well, let's find out what sort of filter we want first of all. I'm going to go to the analog devices filter wizard. So I know from the filter I had before, I had an 8th order filter. I'd like to maybe recreate some of the responses of that filter in my programmable filter. So let's see what we can do. Let's just check the performance of the filter that we had there. So this was a 3 dB point at 1 kHz, and let's bring this down 60 dB down about 2.5K. So off to the analog devices filter wizard. Let's check, see what filter it was. That was a low pass filter. So just Google analog devices filter wizard and you'll come up with this page. We're looking for a low pass filter, so we'll click on low pass. We'll set the gain, the 3 dB point to 1 kHz. And we want to be down at -60 at 2.5 kHz to replicate the filter that we're currently using. Ish, probably closer to 2400 actually. And this is telling us down here that we can build this with an 8th order Butterworth filter, which of course is what we had before, using 4 stages. So let's go back, get rid of that. I'm going to increase the number of stages in this first filter to 4. And you'll see that we've got here the 4 stages of this filter and the parameters associated with it. We want a low pass filter, so I'll just select low pass on each one of the stages. Very easy to make a mistake here and accidentally select the wrong one for one of these, and everything goes a bit strange then. Let's see how we have to set this up. So 1000 Hz is the frequency currently set, but let's see what the analog devices filter wizard says for the stages. So here's the response for our 4 stages, and it's telling us that each one of these stages has got the cutoff frequency at 1 kHz, which is fine. But the Q factor is varying. The first stage is 2.56, so I'll pop that in here, 2.56. Second stage is 0.9, 0.9. Third stage is 0.601. You can't get it quite that accurate. 0.601. That'll come out at 0.6. And the final stage is 0.51. 0.51. Okay, so that's set this filter up, which should now be the same as the other filter. So what we can do is we can take the information from the same source. So I'll put a T connection in. I'll have the same stimulus for both filters. So I'll reconnect that one. I'll also connect it to here. Connect the output. I need another output in order to compare the two. Doesn't really matter because we're not physically using the output. I'll put a second probe in here. Okay. So that's actually a little bit sharper than I expected. Oh, that's minus 15, that's why. So let's get the scale the same for both. Minus 60. So there we are, just over 2 kHz. So this is the same. So we've constructed the same filter out of 4 separate stages. And I think I can probably overlay one on top of the other, but not like that. I'm still relatively new to this, so a lot of these things are sort of trial and error. Let's take that to there. I don't know what's going to happen here if I do this. This is a bit of an experiment. No, it won't let me connect a second output. There is a way of showing both on the same graph, but I can't remember what it is offhand. But anyway, these are both the same. So that's the situation that we're in at the moment. So you have this filter, which looks like that, and the second filter, which looks like that. Okay. So there we have the two filters. There is a way of showing them on the same graph, and I can't remember what it is offhand. But I wanted to move on to another aspect of this programming. So one filter is fixed, one filter is programmable, and we can select that filter, this one, or this one, and you can grow this up to 16 possible filters. So how do we go about selecting the different filters in hardware? Well, we can either use individual pins on the GPIO port, or we can actually use a potentiometer to select the different filters. We have an input here which is the index selection, and so let's just get rid of some of this stuff to tidy things up a little bit, and then we can move on to the next stage. Just move things out the way. Incidentally, let's get rid of this. Just pressing the delete button. These some of these things don't go away when you right click, so you actually use the delete key on the keyboard. Little tip. So we want a potentiometer. Now before we do that, we need to make sure that we've configured the inputs as an analog input. So if I right click on the hardware configuration window on the ADAU1701 and look at the register window, we can see that all of the GPIO inputs are currently selected as input debounced. Now on the Wondom Kernal board, there are 4 potentiometers, and these are connected to input 2, input 3, input 8 and input 9, and we need to configure those on here, or else when we program the chip it won't recognize them. So that's made the configuration correct. That's done that bit. We did use a DAC1 output. We'll revert that to DAC0, which is the output that we've been using so far. And now we have to select the filters. Now if I just look at this probe for a second, and the stimulus, You can see that this is the fourth filter here, third filter, the second. These come pre-programmed, and this is the one that we've built. If we were to build the second filter, let's make that a 4-stage filter as well. This little square in the corner gives us the picture of the filter. We can turn this into a low-pass filter as well. You can see as I add the components, it has an effect on the shape of the curve. I'm not going to worry about actually building that filter right now, just to prove that it can be done. So we need the potentiometer to give us our input. So going back to the general purpose inputs, we'll select the input, which is a auxiliary ADC. So we're going to use the analog aspect so that we can connect the potentiometer up. We're going to need a DC input. A lot of these index controls require a DC input in order to work, as far as the drawing is concerned. So we'll select DC input. And the configuration of this is that this is the number of integers and these are decimal places. Most of these things require 28. We have 4 stages, so I'm going to put the number 4 in there, and I'm going to multiply these two together using a multiplication tool in the basic DSP. Connect that to that, and connect that to that, and connect that to the filter. Okay, so I haven't programmed these filters, but it should be possible if I actually turn this one into a high pass filter. Let's turn this one into a 4th order band pass filter. And let's turn the last one. Oh, where are we? Bandpass filter. See what I mean about getting confused and getting these all the same. Bandpass filter. This one I need to go back to, set them back to high pass filter. And the last one I'll make into a 4-stage notch filter, accepting that some of these we won't obviously hear anything at all. Apologies for the delay. So what happens when somebody rings the doorbell when you're halfway through making a video. So let's make this a notch. Okie dokie, so that's the last one done. So let's have a look at the response of these different filters. The theoretical. So that's the last one, which was the notch. That's the previous one, which is now a bandpass filter. That's the high pass filter, and that's the low pass filter. All these are being driven from ADC0, which is one of the 4 potentiometers on the board, and I'm pretty sure I know which one it is. So what we'll do is link, compile and download this to the board, which has now been done. I'm going to turn my radio back on. Generate some noise. I need to plug the board into it. Okay. So if I now turn the potentiometer, one, two, three, four. So those are the 4 filters. 1, 2, 3, 4, which are selected just by turning the potentiometer on the board. So a random selection of filters there, but you can see how they might be useful for doing different things. So there we are. That's the end of this video on programming filters. There are other methods of selection, as I said. Instead of you can use a binary input on here by having 4 of these and using these as general purpose input pins. There's loads of examples from the Analog Devices website as to how to do different things, different interfaces, different inputs and outputs, but this hopefully gives you a bit of an overview into what can be done. And obviously you can cascade these filters and so on and so forth. So that concludes this video, and I hope you've enjoyed it, and I hope the audio was a little bit better than the previous one. Goodbye for now.